Tim. You're muted. You're muted.
I'm sorry, let me try that again. Hi, everyone. Welcome to another Talk Math with your friends. It's my pleasure to introduce this week's speaker, Dr. Malena Español. She's a professor at ASU in applied mathematics, and today she's going to tell us about inverse problems in imaging, something I know nothing about, so I'm very excited. All right, please join me in welcoming Malena.
Thank you for having me here and for the opportunity. Let me share screen. Yeah, I'm assuming you are seeing it.
Looks good.
Let me see if I can do, on screen. All right, so yes, I am Malena Español at Arizona State. And I will I'll start by saying a little bit more about me there. I'm from Buenos Aires, Argentina, a big city. Here I have pictures, so it's really like New York City. And I studied at the University of Buenos Aires. And while I was in college, I did an internship as an actuarial assistant. That was my first job. Although before that, I would say I was also doing tutoring. So I am an applied mathematician, and I have been working doing, as an actuarial assistant, doing many different things. And I want to kind of show you a little bit about, all the different things. In case you don't know, actuarial science is really, no, let me tell you directly only what I did. So this was about trying to estimate how much to charge for health insurance. There was nothing really for Argentina. So we took statistics, some rates from the States, and we used them to estimate and get some values. At the end of the day, it was really a least squares problem. And I will talk about that later on, but it's kind of, something that I use a lot these days. But I started, a long time ago in a different area using them. So in Buenos Aires, at the University of Buenos Aires, really to graduate, you need to do kind of an honor thesis. So I work in this chemical reaction called the Veloso-Zhabotinsky reaction. It's an oscillation that never ends, right? So you mix things and you will wait for it to stabilize, and it never does. It keeps oscillating, and you can model this by using ordinary differential equations. So by the way, I put maps. So just to show you where I'm from, very down there. Although we could flip the map and put it upside down, as Mafalda, one of our cartoons, said. Anyway. All right, so, and at some point I came to the States. This is my husband, Agustin. He was my boyfriend at the time, and he decided to come to the States. I never really thought about coming to the States, but he decided to come, and that's the reason I came to the States. And I like to say that I follow my love. It's funny, but I'm getting emotional. It's a big decision. It wasn't my dream to come to the States, or didn't plan it. But life happens, and I feel that my whole career and life was like that. Things happen, and yeah. So we took a plane and we went to Boston. I put Med for Massachusetts to be more precise, but really we went to Boston, really, Boston area. So I was trying to get jobs, and then someone suggested me, why don't you do a PhD? And that's how I kind of ended up doing a PhD. Didn't really plan to do a PhD. In Argentina, if you want to work as a mathematician, it's not that you really need a PhD. And I want to say something that I think is very uncommon, but my father met a mathematician in industry, and that's what I thought of a mathematician since I was very young, that the mathematician could solve any problem, go to any industry, any company, and solve problems. So for me, as a, I wanted to study applied math, and that's what I did, but thinking that I will go to industry and solve problems. And so you don't really need a PhD to do so. So it wasn't in my plan. It wasn't my goal. But someone suggested, why don't you do a PhD? And that's what I did. I applied, I got accepted, and I went to Tufts University, where from even before it started, I went to Tufts to know the faculty there before deciding if I will go or not. And I met my research advisor there, and her area of research was image processing, in particular image deblurring. That is what I did, and I will talk today about that. And everything I know about that, I learned from her. After that, I went to Pasadena, California. So I went to from the East Coast to the West Coast, and I went to Caltech, and I work in materials modeling, totally different. This is computational solid mechanics. I gave a talk recently, and someone asked me, if I pick topics. I wasn't really looking for a particular area, but I wanted to do I wanted to do simulations. And so this was an option. So I went to Caltech, where I ended up actually doing very theoretical math, proving some theorems, and learning a lot about electronic structure of material, how materials deform, and learning a lot of different math. So the math that I will talk today is more related to the numerical linear algebra, what I did for my PhD. But when I went to Caltech, I had to learn a lot about calculus of variation, other things. But as I, when people ask me, what about changing topics? Yes, it is it's difficult to change topics. You have to learn about new areas, but I like to learn, and I like to solve problems. So why not? It's really nice to be able to solve problems. So that's what I did. Then I got a position as an assistant professor, a tenure track position at the University of Akron. So I moved across the states again. And there were faculty already working in materials. And I guess that's really why I got hired, because there was a group already working in modeling materials. And there they were trying to understand how layers of graphene interact, and how you can model that and get these patterns that appear here, depending how much you rotate them. There I also work in medical diagnosis. As you can see, very different areas, and I not regret anything. I learn tons, and I keep learning, and I keep changing. So at the end of the talk today, I will tell you what I'm doing these days. That it might not be so different from what I have done, but I like new challenges. I got tenure at the University of Akron, and I became an associate professor there, but I got the chance to go to Arizona State. So I moved there last year, and I'm trying to work more on these problems that I will tell you at the end of the talk. So any questions so far? Nothing? Please interrupt me anytime. All right, so for my PhD thesis, I work in image deblurring. So let me motivate this a little bit. So suppose that you are looking at some tissue using a microscope. So because the microscope has some lens, no matter how much you get closer or the accuracy of your microscope is going to have some blur. So, or for example, let's see, so suppose that now we are looking at the sun, right? Totally different dimensions. And we use a telescope. Again, it has a lens. So no matter if we take the telescope and we put the telescope outside Earth in the, in the space without the atmosphere interfering, it still has a lens. So even if we improve, even if we make the telescope larger and larger, there are going to be always some blurring effect. Okay. So medical imaging, more astronomical pictures. So here I put this one because this is a project that I did when I was a graduate student at the IMA workshop in industry. And the idea was to do reverse engineering, right? If you take a picture of some chips, the chips are very, very small. Even if, trying to get the picture is going to have some blur. So how can you enhance that image? And the idea is, what can we do with these images we have, okay, to improve them, okay? So I'm hoping with these examples, you are like, oh yeah, we really need to solve this problem, image deblurring problem. So before we do that, let me tell you how computers work. This is a picture of my son. Now he's 5. This is when he was 2. I'm reusing my slides. So he was, yeah, I think he was 2 in this picture. So you zoom in, zoom in, zoom in. At some point, you start seeing the pixels, right? But for the computer, each pixel, each square here that you see, it's really a number, right? So you can think about a picture as a matrix. Or you can actually think about this matrix and vectorize it. You can put this whole matrix in a vector by stacking the columns, okay? So you can imagine that, just to kind of simplify, but if this image is 1,000 times 1,000, then this vector is 1 million long. Okay, so I'm giving you these numbers to get an idea of how big the system that we are going to solve, or the system related to images are. Okay, so if we try to do things with the computer, we really care about how to make things faster. Even though we have computers that go faster and faster, we still need to be smart to not wait forever to solve some problems. Okay, so how do we model this image deblurring? Well, so I'm assuming that this is the reality. This is the real scene that I really want to reconstruct. But it got blurred. So this effect that the lens produced, I will assume that we can model it, but by a matrix. Okay. And here you can have an example of what happens, right? So you can really think that you have a pixel and somehow you put the mountain. I want to think about, where the mountain gives you the weight. So, if you are on top of the mountain, you are that pixel. And let's say the weight is 1, but then you also get the pixels around you also contribute with some weight, right? So the pixel in the middle gets information from the pixels around, and then the pixel gets this blur. Okay, this is an example of Gaussian blur. Okay, there are other kind of blurs, but this is just an example. So I want to think, as I said before, I want to think that an image is really a vector. Okay, so when I write x2, I really want to think that this is a vector, and then I get a blur image, but by multiplying that vector by the matrix A. So here I have a blur image. In reality, it's not the only thing that we have. We actually have a blur and noisy image. And because of this noise, then you will see that this problem is very hard. If we didn't have this noise, we wouldn't be talking about how to solve the image deblurring problem. But because of the noise, this noise here inverting, going backwards, right? Going the inverse process, doing the inverse, right? Starting from this image and trying to get this is not as easy. And I will try to explain why. So just before leaving this slide, let me read what is in here. But basically this problem is giving a blur and noisy image and giving the process that we got us there, giving the matrix A and the right-hand side B, we want to reconstruct this image. That's our goal. As I mentioned, just doing the inverse process, sounds natural, sounds like, okay, let's do that. But when we do that, this is what we get. Something that, is even worse than this blur image. This is all noisy. This is garbage. This is totally useless. So what happened?
Do you know A in general?
Here we are assuming that we know. In general, you might have an approximation. You might be able to estimate, but knowing it exactly, no. But this is the simplest approach to at least try to do something. Mm-hmm. The image deblurring problem is part of a whole family of problems that are called ill-posed inverse problems. That have the characteristic that if your right-hand side of your data is perturbed a little bit, then trying, to going back to doing this inverse process, then the solution is very far from the solution you are looking for. Okay, so all the things that I will talk today about image deblurring can be applied to a whole family of other problems. Okay, so let me tell you about the singular value decomposition. And we are going to use this decomposition to understand why doing just the getting the naive solution, this natural inverse process is not, it doesn't work. Why it doesn't work? So singular value decomposition, it's a product of three matrices. Two of them are orthogonal matrices, and this one in the middle is a diagonal matrix with the entries decaying. But in particular, the problems that we are going to solve have some other characteristics, some characteristics of this decomposition. So here, for example, I plotted the singular values, right? So we have, if this is, the matrix has dimension 1000 times 1000, we have 1000 of these singular values and we can plot them, right? So we plot the values of them. As I mentioned, the entries decay, are ordered in decreasing order, and you can see here that this decreases, that is very common because that's the definition of the singular value decomposition. But what is characteristics of these particular problems is that they decay to 0, and there is no gap. Okay, there is no clustering of the singular values. Okay, and that makes this problem also very hard. Some of these problems might have the singular values decaying faster to 0, but all of them share that they have no gap. Another very important characteristic is the following. And let me tell you how to look at these plots. So each singular value has a singular vector connected to it. Okay, so this image here really represents the singular vector that is related to the largest singular value. And here I'm doing the opposite that I showed you before. When we have the image, I vectorize it, right? So we started with an image, there was a matrix, and then we vectorized that matrix. Here I'm doing the opposite to be able to interpret a little bit better what is happening. So when you look at this, let me go back for a second here. When we look at this matrix V, and if we look at the vectors at the columns, okay, that is going to give us a basis that we are going to use. But to put it in or to connect it to images, I'm taking the first column of that matrix and I going backwards and making it an image. Okay, so I'm doing the opposite of vectorizing, right? So I have a vector and I make an image out of it. So, and that vector is connected to the largest singular value. This one is the second one. So this one is connected to the second largest singular value, and so on. Right?
Malena, we had a question. Mm-hmm. Why would it have been good to have clusters or gaps in the singular values?
Yes, that might be clear in a few more slides.
Okay.
We are going to try to filter and do some things, and if there was a clustering, the way to stop or to find those where you will see it, where to truncate or do something else, it will be easier. Okay. So yes, so here what I want you to notice is that when these singular vectors get more and more oscillatory, right? So the black and white means really that they are changing signs, right? So here is like changing a sign in a very smooth way, but you can see that the things are starting changing more and more often, okay? So for smaller and smaller singular values, we are getting more and more oscillatory singular vectors. And this is very important, and this is very typical of these problems. If you take the discretization of the Laplacian and you look at the same thing, it has the opposite behavior. The singular values are going to be connected to things that are very, very oscillatory, okay? But this order is very typical of this problem. So again, the larger singular values are connected with something smooth. Higher or smaller singular values are connected to very oscillatory singular vectors. So here I want to summarize what are the characteristics again of these problems, not just of the image deblurring, but all this family of linear discrete ill-posed problems. So the singular values decay without any gap. Here I'm assuming that this noise is a Gaussian noise. The singular vectors become more oscillatory. And then there is this extra condition, what is called the discrete Picard condition. And I have this plot here to explain it. And basically it says that if you take this, the true blur before the noise, if you look at this vector and you look at it in the basis given by the singular vectors, those coefficients, looking at those coefficients, so the coefficients of it true in that basis, they decay faster to 0 than the singular values. So why is that important? Let's see. So what I'm doing here is writing the solution, the naive solution, just inverting our matrix A1. Remember that we want to see why we get this noisy solution. So I'm going to write this solution as a linear combination using these singular vectors. Okay? So we are getting a number times a vector plus a number times a vector. So let's look at, so I did this with a particular example. So I'm here plotting these coefficients. Okay? And here I also plot, instead of the vectors, as images, because I love to see this. And I love to tell my students about this, right? Here I'm writing an image as a linear combination of images. And we can do this for whatever we want. We can have any structure as a linear combination of structures. So I really like this example as very abstract for linear algebra, right? An application for linear algebra. So here we are writing this noisy or this solution as a linear combination of these singular vectors. And looking at the coefficients, we can see that this one that is super large, very large, is really the one connected to something that is very, very oscillatory, right? And basically this term dominates the whole solution. So there is no hope to have something nice when the whole thing is dominated by things that oscillate a lot, okay? So why is that? What is happening and what can we do? So what I have here is basically these coefficients decompose in two terms. Because when we look at the terms, remember that B is really B true plus some noise. So here I'm decomposing these coefficients in that part. What is the contribution given by the B true, okay? And what is the contribution by this extra noise that is in our blur and noises image? And we can see that the noise at some point starts to dominate, okay? And the idea is, well, when the noise starts to dominate, let's try to, get rid of those coefficients or do something to them, okay? And that's basically the main idea of many of the algorithms developed for the standard methods to do the image deblurring, solve the image deblurring problem. So again, just looking at this linear combination, we add a weight that is 1, okay, or close to 1, when the noise doesn't dominate, and then kind of close to 0 when it's all noise, okay? That's it, this is it. This is filtering, right? So we are filtering the noise, but just putting an extra weight. So what are these weights? Well, there are different methods. Depending how we define these weights, we will have a different method. So one method, these are very, very standard method. One is the truncating singular value decomposition. Basically, you take this expansion and you truncate, right? You keep the first K terms. This is equivalent to say, we give a weight of 1 to the first K terms and then 0 to the rest. Or you can just think about truncating that expansion. The other very known method is Tikhonov regularization, where the weights have this specific form. But you can see that for very large values of sigma, this is close to 1. And then when these are close to 0, well, this is going to be close to 0. How this exactly, what is exactly these numbers will depend on this other parameter.
And just to be clear, it's because you don't know where the error crosses the other one that you sort of, okay. Because there was
Yes.
a question, how did you plot the noise in the previous graph? That was just something you made up, right?
Right. Now that I'm, showing you pictures and things, these are toy problems. In reality, you don't know. Sometimes you can estimate the level of noise, but in reality, you don't have that information. So how you find this K, right? So if your singular values were clustered, this will be easier, where you truncate. But because there is no, there is this continuous decay, I mean, deciding where you truncate, that makes it harder. Okay, so I want to focus in the Tikhonov regularization method. We thought about this method as a filtering method, looking at this expansion and saying, let's incorporate some weights. These weights have certain form. Now this solution, okay, is the same as the solution of this minimization problem. Okay, this is a different way of looking at this problem, or this solution. So how can we interpret or read this? Well, so we want to solve the system of equation, AX equal B, that's our model of what is happening. So we want that to happen. Our solution, we wanted to solve that. But we saw that if it only solves that, then we get this noisy solution. So we want to incorporate an extra condition, and that is to ask that the solution is bounded. Let me go back for a second to here. If you want to compute the norm of this, well, you can imagine that it's going to be large, okay, because of these terms here, these coefficients. So if you enforce the whole norm to be bounded, to be smaller or as small as possible, somehow you are saying, I don't like these ones. I don't like the ones that get these very large coefficients, okay? So asking the solution to have a norm, a small norm, is another way to saying, I don't want this, okay? I don't want these large norms. Okay, looking at this problem this way, then you can expand and say, well, maybe I'm not that, just asking the solution to be bounded. Yes, it looks like a good condition, but actually maybe you want your image to be smooth. So you can incorporate that condition here. If you think about L as the discretization of, let's say, the first derivative operator or the second derivative operator, asking this to be small, it means that you don't want chance, right? You want this change in your image to be smooth. And you can incorporate that. And you can incorporate actually any condition that you want, right? So thinking about, not just about image deblurring, but about any other kind of problems, these ill-posed problems, you can incorporate here extra information that you know about your solution, okay? So I want to emphasize, but it's really nice to, get an idea or think about this filtering solution. We understood why the noise was getting there, so we need to filter the noise. So thinking about that, we need to filter, but the same solution, thinking of that is coming from a minimization problem, it brings us many other ways of rethinking this problem and incorporating and looking for solutions. Okay. So we have a parameter here. How important is this parameter, right? Because for each of these, you will have a different function to minimize, right? So for each lambda, you will have a different answer. Okay. So here I'm just playing around. So lambda is 0.001. And then I keep changing lambda, and you see that the solution is different. So it keeps changing, so it's very relevant. What is the value of lambda? So we talk about the finding k when we truncate. Here I'm talking about how, what is the value of lambda? So if lambda is too big, it's giving a lot of value to just not so much the fit in terms of the equation, but more importance to the regularization part, right? This extra constraint. So that's not good either. So how do we find lambda? Okay, there are many standard ways of doing it. For example, as I said, if you have a lambda fix, you can solve your problem, get your solution, then compute what is the norm of Lx and what is the norm of Ax minus b for that solution. And these are numbers, and those you can plot. So you can see, you can plot this curve, and then what you would like is the lambda that makes both as small as possible, right? The ones that are both small, right? Having only, a solution that fits the system, but it doesn't have the condition that you want, or one that has the condition that you want, but it doesn't fit the system, you don't want those. So this is one way of getting the lambda, and there are other methods. But today I want to talk about one particular method that I developed with a colleague about how you can learn, if you have some training data, how you can learn this parameter. And I really like to, for me to understand what's going on, I need to go to the basics, right? Where, what things I know, where this fits. And so I like to explain it in this very simple way. Because learning from data, I put here, learning from data, right? It's something that, you will think about machine learning, etc. But this is something that we have been doing forever, actually, right? When we do curve fitting, we have some data, and then we want to find a model that will help us to predict new points. Of course, going from curve fitting to machine learning, the dimensions of our data is what makes the difference. But everything is here, right here. All our ideas are right here. So what is curve fitting? Well, most of you will know that. Let's go through it. We have points. In this particular case, I want to find a line that goes through zero, right? So I really want to just find one parameter. So I want to find the line that fits this data, right? So I want to find a line that, will predict something that is close to the data that I have, the Y value that I have. And we want the line that fits, that minimizes all these errors altogether. So we write that this way, right? So we want, this is the difference, is the Y that will give us the line and the Y that we have from the data. And we want that difference to be as small as possible. Of course, we usually will have the absolute value, but that is not differentiable. So we use the square here. And this is what we call the least squares problem. I want to rewrite this a little bit different to introduce how we think about this problem in image deblurring. And I want just to write it this way. I want to write, basically I want to write this, the prediction minus the data, but the prediction is coming from here, from this line. I mean, nothing really, nothing fancy here. All right, but I like to write it this way because now we go back to our problem. And this is my collaborator, Julian Chan, and I did this project with her. So we go back to our problem. We have some data. So I want to assume that we have some true images and some blurred images. And I want to find the parameter lambda, just one parameter. such that the prediction that is really a Tikhonov prediction, we can call it, minus the true solution. So we want that to be as close or as small as possible for all our data. Okay. Of course, that this prediction is not a line, just a line. This prediction is a minimization problem. Okay. So, but I hope you can see this similarity with really curve fitting, right? We want to minimize this error where our prediction is coming from some model, and our model here is this Tikhonov model. Okay. So more information if you want, or you want the details, I will give you more details about this. But here you can see these papers. I will have to hurry up. This is the problem. This problem is called bi-level optimization because you have two minimization problems, many papers related to this. But if you use the two norm, okay, the solution, the Tikhonov solution actually has a closed form. Okay? So because of that, we can plug in and put it in the outer minimization, and then we have only one minimization. So there is what is called the generalized singular value decomposition. And notice that before, the singular value decomposition, although we use it also to create methods to filter the solution, I really want to think about the singular value decomposition before as a way to understand the problem. Although at the end, we use it to create filtering methods. This is an extension of that decomposition when you have two matrices. Okay, I won't go too much through this, but basically we reuse these two, again, write our solution, but now we are using a different basis, right? Instead of using the basis given by the singular vector of the singular value decomposition, here now we will have another basis that is coming from information of A and L. Technicalities here. I will skip some because, I don't want to really talk about these papers, but just showing you ideas. So let me kind of, numerical, right? In general, we try to show, when this works, when it doesn't work. And to test this, you create training data in an artificial way. We just want to understand that this method is working, right? So you can create some training data. So here, this is a 1D. Instead of thinking about two, images, you can just take columns of this and you already have the vector that you need. So you can take some columns here, create some data, blur it, add some noise, and then with this training data, find a lambda that works for all of them. And then you create some validation data the same way, and then you see with the data that the lambda that you learn, how it performs. So if you use that lambda for your Tikhonov predictions, how your Tikhonov solutions are from the real one. All right, any questions about this? Because I really want to jump and keep going to other things, but any question?
I have two, and if they're not short, then you can skip them. One is this, so are you training in the sense of like learning how this particular lens distorts things, and therefore any other pictures from the same lens, you can use that lambda? Is that what lambda? Okay.
Yeah, so lambda is, if you do Tikhonov and you will need a lambda, is this lambda with certain picture that you learn using certain pictures? And of course, the blur is going to be the same for everything, from the training, for the validation, for new images. The A is going to be the same. But yes, you want to find a lambda that once if you have new image, you don't have to go through these methods where you know, this L curve for a specific image. No, you already have the lambda.
Great. And then your images were mostly black and white, and it's easy for me to imagine black and white as a one-dimensional kind of parameter. If it's color, is that just sort of like replacing each cell with like 3 or 4 dimensions in the subcolors, or do you have to like take in the geometry of a color circle or something like that?
No, great question. So yes, so in general, the images are it's like 3 matrices. You can get any color as a combination of 3 really colors, the red, the green, and the blue. So you really have, each image is really like 3 matrices, and you should do this, whatever we are doing for each channel. But there are new tools, and I might move in that direction with my postdoc, which is you can use tensors and think about things in 3 dimensions directly. So instead of having, that will be another talk.
Great, thank you.
Well, some
can
results,
I ask a question?
Yes.
In the previous slide, you said that you didn't take the full picture, but only columns. Is that like you only took a part of the image and trained on top of that?
Yes, so this example that I put here is just, so this is just the 1D. So I'm really doing kind of signal deblurring. Right, so I'm not taking this as picture. And I didn't include in this presentation when you actually take the 2D version, but.
Okay, thank you very much.
Let's see. Well, just to give you a flavor of other problems, this is what is called active illumination system. And the idea here is that we want to see how light behaves in a certain scene. So that, for example, if you want to create, this is really used for virtual reality. If you want to create things that are not real, but look real, right? It's really important that the way that things react to light are modeled correctly. So the idea is, you put a scene here, and then you project with a projector some lights, some patterns of lights, which basically can be described as a matrix. So imagine that in each of these entries, there is a bulb that you turn on and off. And then, you pick a pattern, you project, the light reacts, and then you take a picture, and then you capture that picture. Okay. And we assume that the relationship between the projection, what the light that you project, and the picture, the relationship is linear. Okay. So I want to describe how the light behaves basically by a matrix. And that's what is called the light transport problem, right? My unknown is really this matrix that, again, it will describe how the light travels. Okay, just to give you an idea, if this is a 1,000 times 1,000 picture, and let's say that this is just 10 times 10, then this vector is 100, and this one is 1 million. But then here we have the unknowns is basically 10 millions, right? So we are trying to get these 10 millions of unknowns. Okay. This is a project that I'm doing with Suren, Surya. And these are 2 students, Mohit Malu and Bashir, I'm doing. So they are working right now in this project. All right, so again, I hope I gave you an idea that this is a huge problem, right? Because you keep taking pictures. Actually, the idea here is that you take, you project, you take picture, you project, you take picture. And because this has 10 millions of unknown, you really need, so let me just say, if you, if you project using the the standard basis, basically one light at a time, notice that here, if you put, let's say the 1 and all zeros, that gives you the first column, right? So the first column of your matrix, right? So if you do one bulb at a time, the image is basically give you that column. Okay. So in particular here, you will need 100 of these projections. Okay. But we want to reduce all that costs money. You are projecting, taking pictures, projecting, taking pictures, time, storage, and storage is a lot of, it's a big problem. So we want to reduce the number of projections, we want to reduce the amount of storage and reduce the number of computations. So just to give you just a flavor, because I think we are running out of time. But notice that even though this is how we wrote it, or I wrote it at the beginning, I want to change this and say, I'm going to vectorize T, and there is always a matrix L that makes this equal. So here I have the matrix T times L, and I can change the order and find a matrix L such that L times T is the same as this, okay? Anyway, I want to do that because then if I write it that way, then it really looks like the standard least square problem. And whatever we know about least square problems, we can use. Here in particular, let me see. Details, these are details, don't worry. But let me just give you an idea, or one more idea behind this. I don't know if you ever heard about multi-grid methods, and that was related to my PhD thesis. So I'm using kind of the ideas that I applied there to this new problem. And multi-grid is related to the following. If you have a PDE and you need to discretize, you need to pick points. And let's think about 1D, right? So if I have 1D and I need to discretize, I could say, well, I will use 10 points, or I can use 100 points, or I can use 1,000 points. Of course, if we use more points to discretize, the matrix that is going to be related to that is going to be larger. So multi-grid has this idea that, this idea that if you use small points, maybe you can solve that small problem, get some information, and then now use 100 points, but use the information that you already learned having used only 10 points. And then you discretize with 1,000 points, but again, you use already something that you learned using 100 points, right? So you can think about that you have this sequence of problems, okay, where they are relating between the, related to each other, and use the information that you probably gain in small systems. So, well, let me just say, I'm jumping, so if there is no question, then it's okay. But basically what we are doing in this problem is, we project, we get an image, we can compress that image and make it smaller and kind of compress the whole system and solve it, okay? Get some solution there, project again, compress the image, solve a small problem, and update our previous solution, and so on, okay? So, sorry, here I'm jumping and not really giving you all the details, but my goal is really to see that these things that we can think in our brain, like, and get some ideas, then we can formalize them, and actually formalize them in a way where we can use math that we already know. Okay. So, and I think I will end up, some results, but some results here. Yes, let me see. I have okay, let me just say 2 minutes. Inverse problems other inverse problems. So I talked about this one already, but here there's another inverse problem where basically you have an object, you shoot this with rays, and then somehow you capture some images, right? So this is an inverse problem in the sense that you have an image and you're trying to see what are the characteristics of this material. At the end of the day, you can write all these and all the physics, and here and there might be integral equations, but when you discretize them, they become system of equations. So, but it is an ill-posed problem, so you need to add a regularization. So once you rewrite all these, the math or what you need is to solve a Tikhonov problem. So even though this problem is totally different, it still has many of the characteristics of image deblurring. And the other problem I want to just mention very quickly is electrical impedance tomography. You put electrodes around the body, you send some current, you measure some voltage around the body, and then you want to reconstruct what is inside. To model all this, you use partial differential equations, the one which you discretize, and then you end up with a system of equations, and then a least square problem related to it, and then you use Tikhonov regularization maybe to solve it. So very different problems, similar characteristics, and the math, at least that I use, is all the same. So I think I'll stop there.
Please join me in thanking Malena. Yay. We're going to do two quick announcements, and then we might have time for a question. The first one is we have a talk next week. Emerald Stacy is going to talk about differential calculus without exams or prerequisite courses. We're sort of acknowledging as higher education the problematic ways that placement and prerequisites are filtering students out of their paths, especially students of color. And so really thinking carefully about how we want to do that differently. And I think she's going to provide a model there that pays attention to things like managing group power dynamics in the actual class work environment. And then the other announcement is it is Black in Math Week. And if you're not aware of that, you should check out this Twitter account at Black in Math and follow them and check out all of the stories that are being shared. It's really important and interesting stuff here. So I'll just go back here. And one more time, can you please join me in thanking Malena?